Okay, so now I'm going to talk about one of the topics of absorption that it's a little bit advanced, which is when we need to recirculate the solvent. So why do we want to, or how does it work, first of all? So we know that we have the column. So we have the column like this, right? But sometimes we already have the column built, or I mean, it comes from another process and you don't want to simply throw it away, so you're going to install the same column, and maybe it's too big and you want to still use this liquid here because it's not, let's say, good loaded, so it still has space for a lot, or at least for more particles, or more molecules of the gas that is coming up, right? The one that you want to remove. And this is going to generate, of course, after this we have usually some regeneration of the solvent. And if, let's say, if you passed a lot solvent with few amount of liquid of particles, then it's going to be energy and money wasted. So what we are going to do is that we are going to use, so part of this is going to regeneration and the other part is coming again back to the process. So we simply combine the let's say end solvent coming to the process, so in, let's say, with this end solvent that is recirculated, and this is going to be end solvent that simply leaves the process. Okay. What we need to keep in mind is that of course, due to this absorption, there are some heat generation in the column. So if we think about the profile, the temperature profile of the column, it's going to be something like this is going to be the temperature, this is going to be the height of the column. So at the very top, we are talking about the solvent, right? At the very top of the column, the solvent has some temperature, let's say, I don't know, 10 degrees Celsius or something like that. And then while it goes down, the temperature increases, right, till a certain point. That means you would need some cooling unit here. So okay, that's something I wanted to say as well. So this amount here recirculated, we are going to call it the MR factor, which is going to be the recirculation factor, which is of course what you recirculate over what leaves the process. This is very similar to distillation. Okay, so far so good. There are many things to say here about how to derive the equations, but I mean, I won't derive these equations here because I mean, that's something you can find in the books. At the end, I just want to show you how to use them. That's the main purpose. So okay, something important here that I forgot to mention is that this composition here is going to be so we said, for instance, this is pure solvent, and you have some solvent that it has some loading here, right? Some particles here, but not totally. When you combine them, you're going to have this with, of course, not pure, but with some, but not that much as here, because you're kind of diluting these particles. So after doing the mass balance and component balance around that point, that mixing point, you will get that Hm is going to be equal to Hin plus Mr out over Mr plus 1. Of course, let's say if you are not recirculating anything, this goes, and you get just Hin, right? And then yeah, so how is this operating line for this process? Because at the end let's say you have your equilibrium data and you know how much do you want to produce here, right? So you know how much you want to produce there, you know it's M because you know how much you are recirculating. Definitely you can measure that. So my point is, if you have, let's say it's in here, okay, it's in, of course, is this one, okay, this one. If you increase your MR, you are going to be closer and closer to the equilibrium. So this is going to be the maximum MR maximum. Okay, this is important to know. And here you know this point as well. So basically what you're doing if you increase MR is going closer and closer to the equilibrium, but at the bottom, which is opposite to the minimum reflux, minimum amount of solvent calculation. Okay, so how you get the equation of this line, because we said this is a line though. So after doing some mass balances and stuff, you're going to get that Y is going to be equal. This is very, very similar. Wait a second, I have it here. I believe, yes. It's going to be MR plus 1. Okay, let's remember first the other one. The other one was X minus X, let's say in, right? We know it's in usually, times the slope, and the slope was the amount of liquid, of course inert, over the amount of gas. This is usually like that, liquid over gas, or yeah, inert as well, plus Y out, right? So what's the difference here? This term is different, and then here we are going to have same slope, I mean kind of same, because of course it's been modified by this term, and then X minus XM, we know what XM is, plus Y out. So you can see difference. Let me see if I got it correctly. Yeah, exactly, that's exactly what I have here. So this it's let's say more general than the one I have here below. So this is even better. If you have no recirculation, you're going to end up with this one. What else I need to explain about this? Yeah, basically that would be all. So one of the tasks could be like how much can you, or what's the maximum MR to get a specific composition. You know, a specific composition, of course, we said this is the top, so a specific composition at the top, you know, what is the maximum that you could use. Then you will need to of course calculate that using this line equation, knowing the other parameters that you can measure, for instance. Yeah, and that would be all about this advanced topic, which, as you can see, it's a little bit easy, but it needs to be let's say analyzed carefully. If we increase the MR, we're going to increase the amount of stages. And let me see one thing here, because I'm not really sure what they call here, L0. Yeah, let's say that would be all, right? Let's say just L0. Yeah, that's all. So yeah, I hope this is useful for you.